Welcome to the second part of the lecture about robustness of complex networks. My name is Piet van Mieghem and I'm a professor at the Delft University of Technology. In this second part, we will elaborate on how to analyze, how to define network properties and how to measure network robustness. We will focus on the graph theory, which was introduced earlier. A graph consists of a set of n nodes and a set of L links. For example, an airport is a node in an aviation network and the links represent the air routes. Nodes in traffic networks are train or bus stations. Correspondingly, roads and rails are the physical links. Also, power systems are networks in which the nodes are the power plants and substations and the links are transmission lines. Here is an example of a graph. We can map any infrastructure or network to its nodes and link representation. Although nodes and links are generally different, we start by assuming that all nodes and all links are the same. Next, we use graph theory. Any network can be represented as a 0-1 matrix called the adjacency matrix. As an example, we have drawn a small undirected network with n is 6 nodes and L is 6 links. The nodes of these networks are represented in both the rows and columns of the adjacency matrix. When there is a link between node I and j, then the matrix element A sub ij is 1. When there is no link, that matrix element A sub ij is 0. For example, the red link between node 1 and 3 corresponds with a 1 in row 1 and column 3 of the adjacency matrix. Please notice that the diagonal elements are 0 because all the nodes and links cannot be linked to itself. In other words, there are no self-loops. For undirected networks, in addition, the adjacency matrix is symmetric. Once the adjacency matrix is known, the topological properties of the networks can be computed. For instance, the number of neighbors of a node, called the degree of a node I, equals the sum of elements of row I of the adjacency matrix. Besides the degree of a node and the number of links, there exist many more graph properties, also known as graph metrics. Here we list graph metrics. Each metric tells a different story about the graph. This slide is basically meant to overwhelm. The list illustrates that we can study an almost uncountable number of network properties. In the literature, you will find examples. The challenge here is to select that set of most important graph metrics for the infrastructure that you want to assess. Most people attach the concept of network robustness to that of network connectivity. And here we show the algebraic connectivity as a matrix for connectivity of a graph. The algebraic connectivity is the second smallest eigenvalue of the Laplacian of the graph. If the algebraic connectivity is 0, then the graph is not connected. Else, the higher the algebraic connectivity, the stronger the graph is connected. Now, if we measure robustness by the algebraic connectivity, then we can compare different networks. So far, we have concentrated on the topology of the network. However, a network also has a purpose. In other words, the network consists of one or more services. For instance, electronic mail is a service in the internet. The mail application maps your email into IP packets that are transported in the internet from source to destination. The service metrics, such as the delay, the packet loss, the availability, and so on, are more complicated to define, mainly because it depends on the human appraisal. Some people accept longer delays or tolerate more lost packets than others. We omit a discussion on service metrics, and we assume in the sequel that we are able to compute service metrics. With the help of graph theory, we can now express the network robustness by any graph matrix, or more generally, as a certain desired function of a graph matrix. The robustness of the network is then a number, R, the robustness value, or the R value of a network, which we normalize between 0 and 1. A 0 R value means complete absence of robustness. An R value which is 1 represents an ideally robust network. Now, with all these preparation, we are now able to assess how good a network is via the R model. From a network consisting of a service and a topology, we compute the R value. If that R value lies above a desired threshold, called the R threshold, then we call the network robust. If the R value lies below the threshold, then we need to modify the network to increase the R value. The network can be modified by changing the topology, for instance by adding links or removing nodes, and by improving the service, for instance by better protocols or network algorithms such as path computations. Modifying the network implies financial cost, and thus it is a complex optimization problem. A network or a system is not simply robust. A network is robust against something. It is against a perturbation such as an attack or any other challenge as a random failure, for instance. The definition of robustness is too restricted if it does not take into account the attacks and challenges that progressively degrade the network. Here we can see three behaviors for three different networks. A strong, always on top, a stable but low, and a weak, a rapid decay in the R value. There is a huge number of ways in which we can attack a network. First, we see 10 different realizations, 10 different ways in which subsequently a link in the network is removed and its effect on the R value. We now see the probability envelope as a contour plot consisting of all possible ways in which K links can be removed. So the blacker the region in the contour plot, the more realizations return this R value. The outer boundaries of the envelopes are the contours of maximum robustness and minimum robustness over all possible attacks or network challenges. Here, on this slide, we formalize how quantitatively to evaluate robustness as a function of the attacks. The red area measures the overall strength or energy. The larger the area, the better. The blue area measures the overall sensitivity. The smaller, the better. The blue area contains most, say, 80% of all realizations, and the narrower the blue band, the smaller the uncertainty of an attack to the R value. Robustness envelopes allow us to compare networks with each other and allow to evaluate different attacks. Here we see our robustness envelopes in action. The graph A on the left is an Erdős-Renyi graph. It is hard to disrupt, the sensitivity is high, the area of the contour plots is small, and the energy is high, the area below the contour plots. Graph B on the right is an European power grid. It is easy to disrupt. In summary, we can clearly quantitatively show that this network is weak. It is not robust. Challenges can be either random failures or targeted attacks. The contours in the robustness envelopes reflect the probability of a certain attack strategy. Here, different attack strategies are compared on the Erdős-Renyi graph and on the Barabasi-Albert graph. As R value, as robustness value, we have chosen the efficiency, which is the average inverse hop count of a path between two nodes in the graph. For example, the red curve shows the subsequent removal of the highest degree nodes. The light blue one shows the subsequent removal of the highest betweenest nodes. and the yellow-orange line shows the subsequent removal of nodes with highest principal eigenvector components. Thus, the color lines represent a certain attack strategy. The effectivity of a certain attack on the chosen R value can be assessed from the contour plots. For example, the red line, the highest degree removal, is close to an optimal strategy to destroy the Barabasi-Albert graph, whereas the between strategy is the more successful strategy to destroy an Erdos-Renyi graph. To summarize, we've shown that infrastructures are vulnerable and that the robustness theory of complex networks is needed. But an overall accepted definition of network robustness does not exist yet. However, the R model works, provided a network robustness value, the R value, is defined. A network is robust against challenges, such as random failure or attacks. Network robustness envelopes allows us to compare the robustness of different networks and the impact of an attack strategy. Thank you for your attention.